Welcome back, everybody, to Probability and Analysis webinar. Today, it's our great pleasure to have José Ramón Madrid Padilla from UCLA, who is going to talk about generalized Collatz maps. Please, José, feel free to start.
Thank you, Pata, for the nice introduction, to all the organizers for the invitation, and to everybody for coming. So yes, I would like to talk about a generalized class of Collatz maps. So the starting point is, of course, the usual Collatz map, which is defined in this way. If n is even, we divide by 2, and otherwise, if n is odd, we multiply by 3 and add 1. So for a fixed natural number, we can iterate this map several times. If we do that, we obtain a sequence like this. And this is precisely what we call the orbit of capital N. In particular, if we start with phi, this is what we get. So we can observe that after a few steps, we obtain 1. And if we start with 7, this is the orbit that we obtain. Again, after a few steps, we can observe that 1 shows up. The conjecture is precisely that no matter what is the starting point, eventually 1 shows up. So eventually the orbit reaches 1. And once we obtain 1, we are inside of this cycle, 1, 4 to 1, 1, 4 to 1, and so on. Okay, so in principle, when you see this map for a first time, you may think, oh, maybe I will try a few values to see whether or not the conjecture is true. But that's perhaps not a great idea, because even for a small value like 27, you can see that you need more than 100 steps to obtain 1, to reach 1 for a first time. And at some point, the orbit of 27 get as high as over 9,000. So this shows a little bit the difficulty of this problem. Some other interesting facts that I would like to mention are the following. Another attempt that you can try in order to disprove the conjecture will be to try to find another cycle different than this one. So you can try to find a cycle starting at x, finishing at x without passing by 1, right? If you can do that, you can disprove the conjecture. Unfortunately, that's also, that will be very difficult, because it has been shown that in case that a cycle like that exists, the length or the size of that cycle will be super large, over 17 millions. So another interesting fact is that it has been verified computationally that for every natural number smaller than 10 to the 20, the conjecture holds. So there is a lot of evidence that suggests that the conjecture should be true. Okay, so 3 years ago, there was a very nice paper by Terry Tao, and in one of our meetings, he suggested us two questions. One of them was, okay, so he got some interesting results in terms of logarithmic density. I am going to be more precise about that later. And he said, oh, one question you can consider is you can try to obtain a similar result in terms of natural density. That will be stronger, because natural density implies logarithmic density. And the other question he suggested was you can consider a larger family of Collatz like maps and try to see when those maps behave nice and when those maps behave in an erratic way, right? So when are we able to say something interesting about some other maps related to the original Collatz map? So this talk is about the second question. So we got some interesting results in that direction. And of course, if we want to consider some other maps related to the original Collatz map, a good starting point will be this one. Here we have the only difference between this map and the original Collatz map is that here we have -1 instead of +1. In principle, you may think, oh, probably something very similar to the original Collatz conjecture holds. That's not quite true in the sense that we can easily observe that it's not true that for every natural number, the orbit eventually reaches 1. In fact, it's super easy to find a counterexample. If we start with phi, after a few steps, we are back to phi. So this is a cycle that does not contain 1. However, what we can conjecture in this case is that there are only 3 cycles, such that for every natural number, the orbit eventually reaches one of these 3 cycles. This is one of them. Another cycle is this one. If we start at 17, after a few steps, we come back to 17, and the other cycle is the one that we obtain when we start at 1. If we start at 1, we obtain 1, 2, 1, 2, 1, 2, and so on. So it is believed that those are the only 3 cycles. And no matter what is the starting point, eventually we get inside of one of those cycles. Okay. Here we have another example that I would like to discuss. So let's consider this map. We divide by 4 when possible, and otherwise we multiply by 3 and add j, where j is the residue of n mod 4. So what can we say about this map? Be aware that, okay, let's consider this case. If we choose a natural number which is not divisible by 4, so capital N looks like this. If we apply this map 1 time, this is what we obtain. So the image of n is equal to this. And if we apply again, this is what we obtain. So since this is divisible by 4, we obtain 3 times k plus j, which is strictly smaller than capital N. So this means that after 2 iterations, we always get something smaller than what we had originally. So these maps are easy to handle, right? Because they are contracted. In particular, if we start at 11, we observe that after 2 steps, we get 9, which is smaller than 11. Then we get 7, 6, 5, and so on. So in fact, is there any question? I can see that someone raised his hand.
I have a question.
Oh, sure, go ahead.
Yes, about the previous slides. If you could place that one. Yes, yes, this slide here. The portion that says 3n minus 1,
Yes.
that is for a typical odd number. However, the question that I have in mind, the general definition of an odd number is 2n plus 1, for example. What proportion of 3n minus 1 is it compared to 2n plus 1 within the range of the within the range that you're in place using? Are there more 3n minus 1 than 2n plus 1, or they're about the same? I mean, is there a proportion in general between the
yes,
two?
that's a very good question. In fact, so we are going to discuss a more general class of maps, right? I just thought that it would be a good idea to go over a few basic examples at the beginning, which is in fact the way we proceed in this project. So this is like a historical overview of what we did, or what we started thinking at the beginning. But yes, that's a very interesting question. To be honest, we didn't spend too much time. I haven't seen that much on that, but that will be very interesting. We have some numerical evidence. Maybe I can say more details about that later. But in principle, yes, I will need to think before to give a good answer to what you're asking for. Yes. But yes, that's interesting. What to understand that more precisely. Yes.
Okay.
But anyway, so so I was going over this second example. So what I mentioned is that in this case, since we observe that after 2 steps, after 2 iterations, we always get something smaller than what we had originally. Then this map is very easy to handle. In fact, we can easily prove that in this case, the orbit of any natural number eventually reaches 1, 2, or 3, and then we are in a cycle forever. And the reason why this map is very easy to handle is because 3 is smaller than 4, right? And in the original Collatz map, we have 3 and 2. 3 is larger than 2, 3 is small, and in this example, 3 is smaller than 4. So if we consider so soon I'm going to discuss a more general class of maps. We will divide by p when possible, and otherwise we will multiply by q and add some r. So we will. So the interesting case, the interesting situation is when q is larger than p, because otherwise we are going to have some contractive mapping, and those are very easy to deal with. Okay, if at some point there are more questions, feel free to ask, of course. I will be happy to try to answer. So here is another example that I wanted to mention. Let's consider these two maps. C1 and C2, they are defined in this way. Here we divide by 2 when possible, and otherwise we multiply by 5 and add 1. And here we divide by 3 when possible, and otherwise we add j, where j is the residues of capital N mod 3. Okay, so let me talk about C1 first. The only difference between this map and the original Collatz map is that here we have 5 instead of 3. And if you have no experience thinking about this problem, you may think at first that this is very similar to the original Collatz map, so probably this behaves in a similar manner. However, that is not the case. It turns out that the orbits of C1 are very erratic. In particular, if we start at 7, it is currently unknown whether or not this sequence is bounded. So it seems that the orbit of 7 goes to plus infinity. And for instance, after 1,000 iterations, we obtain this super large number. So this map C1 does not behave well. On the other hand, this map C2 behaves really nice. There is a lot of numerical evidence that suggests that no matter what is the starting point, eventually we always get inside of one of these two cycles. Okay, so this is related. Okay, this is going to be clear later, but this is related to the fact that here phi is larger than 2 to the 2. And here, phi is smaller than 3 to the 3 half. 3 to the 3 half is a square root of 27, which is larger than phi. So that plays an important role, but that's going to be clear later. Okay, this is a more general class of Collatz maps. And this is, in fact, the class that we study. So if we have 2 coprime integers, p and q, so let's assume that q is larger than p, because otherwise we have some contractive mappings, and those are easy to handle, as I explained before. We will choose some rj's such that this number is always divisible by p. And we define this map C in these ways, in this manner. So we divide by p when possible, and otherwise we multiply by q and add rj. Be aware that if capital N is not divisible by p, so this is the image is going to be this. But then in the second iteration, we will divide by p, right? So because we choose rj in a convenient way, right? This is to avoid, because if we don't do that, in principle, the orbit could increase faster, right? And we may have a more erratic behavior, right? So this makes sense for us. I should point out also that if, of course, if p is equal to 2, q equal to 3, and r is equal to 1, we recover the original Collatz map, right? Okay, something which is also useful and it's a good idea to keep in mind is that we also consider this map that we call an acceleration map, capital S, which is defined in a similar manner, but basically, okay, so we divide by p when possible, but more basically what we do is that in this case, we will divide by the largest power of p. In fact, here there is a typo, but basically we will always divide by the largest power of p. So this m is basically the p-adic valuation of this number, q times n plus rj. Okay, so basically we can observe that for every natural number, the orbit of capital N by the map S is a subset of the orbit of capital N by the map C. We can also observe that the minimum here in the left-hand side is equal to the minimum in the right-hand side. We can also observe that saying that the orbit of N through this map C eventually gets inside of a cycle is equivalent to say that the orbit of capital N by this map S eventually gets inside of some particular cycle. So these two maps, they behave in a very similar manner. we call capital S an acceleration just because this moves faster, right? That's what clearly we have this inclusion. Okay, so let's try to keep in mind these maps, because this is precisely the family that we study. I'm going to state our main theorem in a few minutes. But before that, I would like to say a few words about some interesting observations by Conway. So there is a well-known computer language called Fractal that was precisely created by John Conway. In this computer language, every program is a variant of the Collatz function. Every fractal program can be described by a finite set of fractions and some initial input, some positive integer n. So there are basically two rules, two operations to keep in mind. But the best way to understand this is perhaps using an explicit example. So let me talk about this particular fractal program, which is called prime, which is given by this finite collection of fractions. Okay, so here we have these fractions. And as I mentioned, a part of a finite collection of fractions, you need some initial input, right? In this case, we will choose n equal to 2. So what we do is we observe that 2 times the first fraction is not an integer. So we forget about that. Then 2 times the second fraction is also not an integer. So let's forget about that as well. So if we continue like that, we observe that the first time that we obtain an integer when we multiply 2 and one of these fractions is precisely when we multiply 2 and this fraction, 15 over 2. In that case, we obtain 15. So we replace 2 by 15. So 15 is the second element in this sequence. So basically, that's precisely what is written here. The first rule is that the first fraction f in the list for which n times f is an integer. So whenever we find that fraction, the first one, such that this is an integer, we replace the original input n by n times f, which is what we are doing here, right? We replace 2 by 2 times 15 over 2, so we get 15. Okay, so that's the first rule. And the second rule is that eventually we can get to a point where none of these fractions gives an integer when we multiply by n. So at that moment we stop, right? So those are the 2 rules to keep in mind. And let me just, since we are talking about this example, let me just mention that this example is well known and it is very nice, because if we analyze the powers of 2 that this program generates, we can observe that what we get is that the first power of 2 is the first power of 2 after the original input, which is 2, is 2 to the 2. Then we obtain 2 to the 3, then 2 to the 5, 2 to the 7, 2 to the 11, and so on. So we can see that what we obtain are the prime powers of 2 in an increasing way.
So can I ask you one question?
Oh, sure, go ahead.
Repeat this rule until no fraction in the list produces an integer and multiplied by n. But the last fraction is 55 over 1 in this list.
Yes, well, this is, yes, but we replace, there can be a typo here. Well, I just wanted to illustrate how these 2 rules work. So clearly the first moment when we obtain an integer when we multiply by 2 is this one, 15 over 2. And so that's why we replace these 2 by this 15. And then basically you continue in that manner. There may be a typo here, so I may have to double check.
Okay.
But yes, so those are the 2 rules to keep in mind. And as I was saying, so any program is described just by a finite set of fractions like this. So this prime program gives help to generate prime, precisely because we obtain the prime powers of 2 in an increasing manner. But yes, I will double check this. So I'm planning to check the slides later. So I will double check this to make sure that I wrote the precise fractions. But anyway, so I just wanted to mention this to illustrate a little bit how this Fractal program works. And let me go back to our main discussion, which is about Collatz maps. So there is also a Fractal program. Keep in mind that a Fractal program is just, you may think that a Fractal program is just a collection of fractions, a finite collection of fractions like this one, and an input, right? So there is another fraction program corresponding to that helps to test the Collatz conjecture for some specific value x. So if we start with, so if we want to test the Collatz conjecture for x, we can set n equal to 2 to the x, and then we can use this collection of fractions and the two rules that I mentioned a few seconds ago. So if we apply those two rules, eventually we will get another power of 2. And this y is precisely the image of x by the Collatz map. So basically this generates the whole orbit of x. And basically the Collatz conjecture will be that, no matter what is the starting point 2 to the x, eventually we obtain 2 to the 1, right? Of course. So this will be the conjecture. You can also use this program to try to find a counterexample. You can, if you find a number c that disproves the Collatz conjecture, that means that we never get to 2 to the 1, then the program will run forever, okay? However, there are some variants of the original Collatz map that are for which the assertion that the minimum of the orbit of n naught is equal to some specific value is undecidable. So this whole thing was just to say that for that reason, we focus our attention in some particular family. So if you consider a super general family, so this whole thing was just to say that for that reason, we focus our attention in the particular family of maps that I mentioned a few minutes ago. I will come back to that. Because those maps are amenable for analytic methods, those are convenient for our purpose. Because, and I am saying this because you may think that perhaps you have in mind already some larger family of maps that you can consider. I will come back to that also later. But anyway, let's keep in mind that these are the maps that we are studying, and this is the acceleration map. And this acceleration map also plays an important role, in the proof, in our arguments. So I will come back to that later. Okay. So we want to discuss some probabilistic results related to the Collatz conjecture, more precisely, some probabilistic results related to these generalized versions of the original Collatz map. But before that, let me mention a sufficient condition. So if you would like to prove that the Collatz conjecture holds for every natural number, it will be sufficient to prove that no matter what is the starting point, capital N, so that for every natural number, the orbit eventually reaches to a point which is strictly smaller than capital N, right? So basically you are going backwards. So if you can prove this for every n, then you will be done. That's very easy because you can use a basic inductive argument or some iterative argument. So this will be sufficient to establish the conjecture, right? Of course, the Collatz conjecture is still an open problem. So we don't know how to verify. We are unable to verify this property. However, we can check however, a weaker condition is known to be true. So what I mean is the following. You may wonder, can we prove this statement for almost every natural number? So can we prove that this inequality holds for almost every natural number? The answer is yes. That was established in the late 70s by Terras. And here I have to be more precise. So what do we mean by for almost every natural number? So let me say a few words briefly about natural density and logarithmic density. the natural density of a subset of the natural numbers is defined in this way. So the limit of this quotient, what we have on top is the number of points in the intersection of A and the interval from 1 to X, and below the number of points in the interval from 1 to X, right? So this is precisely the most natural way to define the density of A. This can be written also in this way, and this helps to understand the following definition. For any subset of the natural numbers, we define the logarithmic density of A in this way. So be aware that if capital A is equal to the whole interval 1x here, then we obtain capital X over capital X, which is 1. And here, the same thing happened. Basically, if capital A is equal to the interval 1x, then we obtain the sum of 1 over n from 1 to x, which is essentially log of x. So this is also equal to 1. So let's keep in mind these two densities. So going back to what I mentioned a few seconds ago, Terras proved that this inequality holds for almost any natural number. This is very interesting because, as I mentioned, if you can prove this for all natural numbers, then you will be done, right? By a basic inductive argument. Okay, what does it mean? This, to be more precise, what he proved was that this limit is equal to 1. Okay, which means that if capital X is very large, if capital X is sufficiently large, then for almost every capital N in this interval, we have that this inequality holds, right? Okay, there were some improvements on Terra's result. You may think if the Collatz conjecture is expected to be true, so this minimum should be equal to 1, right? In the case of the usual Collatz map. So you should be able to obtain something better than capital N in the right hand side. In particular, this should be true for the square root of n, for natural logarithm of n, and many other. So you should be able to obtain something better here in the right hand side, right? So these are some improvements from a few years later. This power was obtained. This is already strictly smaller than 1. And then in the early 90s, Correct got this inequality, and this was the best until very recent. I should mention that there are some other probabilistic results. In particular, this is a very interesting one by Kazikov and Lagarias from the early 2000s. They proved that the size of the set of the natural numbers smaller than or equal than x, for which the orbit of capital N eventually reach 1, is at least x to this power, 0.84. Of course, if the Collatz conjecture is true, this should be, we should be able to write here x to the 1, right? So I should mention that this is the best bound so far, the best power so far related to this particular inequality. So an interesting problem will be to try to improve this exponent. Okay, so this is one of the two results that I would like to discuss, but in fact, the second one is the most interesting, the strongest. But anyway, so this is also interesting. So I want to say a few words about this. If Q and P are coprime integers, and we have that these inequalities are true, remember that we assume that Q is larger than P just to avoid contractive mappings. This inequality is very important. This comes from the central limit theorem. But I am not going to get too much into details in this theorem because the second one is stronger than this. So I prefer to talk more about the second theorem. But anyway, so under these conditions, if we define theta to be this, first of all, I would like to point out that since we are assuming that Q is smaller than P to this power, then this theta is strictly smaller than 1, okay? So for every epsilon larger than 0, we can prove that the set of natural numbers such that the orbit of capital N eventually reach to a point smaller than this has natural density equal to 1. Here, in particular, since we already mentioned that theta is strictly smaller than 1, we are allowed to choose epsilon equal to 1 minus theta. So this holds also with power 1, okay? And this in particular, so in the case when Q equal to 3, P equal to 2, and R equal to 1, we can recover the previous probabilistic results that I mentioned by Terras, Alosh, and Correc. Okay, so another, this can be read also, so we can say that for almost any natural number, the orbit of n eventually reaches to a value which is smaller than n, right? Because as I mentioned, we are allowed to choose 1 here, because theta is strictly smaller than 1. Let's keep in mind that this is, the reason why this is interesting is precisely because if you can prove that for every natural number, that will be sufficient to establish Collatz conjecture, for instance, right? Okay. So let me mention a failed attempt. Let me mention some approach which is kind of natural, but unfortunately it doesn't work. Since I mentioned here we can get any power which is strictly larger than this, right? So you may think, so for every, we have seen that if we choose a random integer, capital N, in this interval, then in most cases, so for almost every natural number n here, eventually the orbit of capital N gets inside of this interval, right? And then you can try to iterate this idea, because you can say, oh, we also have that for almost every integer capital M in this interval, the orbit eventually reach a point in this other interval. So you can think, oh, I can try to repeat this several times. And since theta is strictly smaller than 1, theta to the n goes to 0. So this interval 1x to the theta, 1x to the theta squared, 1x to the theta to the 3 will be smaller and smaller. So basically you can try to iterate this argument several times to obtain the Collatz conjecture. However, unfortunately, that doesn't really work. And the reason is basically because the uniform measure in this interval is not transported by the Collatz map, by the Collatz dynamic to the uniform measure of this other interval. Okay, so I should also point out, this is a very natural question. So this is a nice result, but unfortunately, the best we can, so we are unable to obtain something better than n to this power, right? So there are some limitations here, right? Because we would like to, for instance, we would like to prove this also with power 1/2, with power 1/3, or even with natural logarithm of n instead of n to the theta, for instance, right? So we should be able to obtain something better than this. And that's precisely the content of our main theorem, which is the following. If we have P, Q, and R, if we have some natural numbers, in C, the Collatz map C, the generalized Collatz map C, and the acceleration capital S as defined before. So let's assume that P and Q are co-prime, this inequality holds, and this is always divisible by P. So for any function that goes to plus infinity as n goes to plus infinity, we can verify, we can prove that these sets, they have logarithmic density equal to 0. Okay, so let me mention why is this interesting. Be aware that we have a lot of freedom, right? So this function f can be anything that goes to plus infinity. In particular, you can choose f to be the composition of log, as many as you will like. As far as you have a function that goes to plus infinity, you are good. So in particular, we have that this set, the set of natural numbers for which the orbit of capital N eventually reach a point which is strictly smaller than this, has logarithmic density equal to 1. So we can say that for almost any natural number, this inequality holds in terms of logarithmic density, right? Where C mean, of course, means the smallest element of the orbit of capital N, right? This theorem was motivated precisely by a result by Terry Tao from 2019, where he established something similar in the case when P is equal to 2, Q equal to 3, and R equal to 1, which is correspond precisely to the original Collatz map. Okay. First of all, I would like to mention that this theorem implies this, as I already explained, but we believe that these conditions should be sufficient to prove that if we have a map like the ones that we are considering, then there is a finite collection of cycles, such that for every natural number, the orbit eventually reach one of those cycles. So eventually, there is a finite collection of cycles such that the orbit of any natural number eventually gets inside of one of those cycles. So we believe that these three conditions should be sufficient. We can ask also about, we may wonder about whether or not they are necessary. It turns out that it seems that they are not. So at the end of our project, at the end of our paper, we include a couple of examples that help to illustrate that apparently they are not necessary. So it will be very interesting to find the precise set of conditions or hypotheses such that they are sufficient and necessary. So as I was saying, we strongly believe that these are sufficient in order to guarantee that this generalized Collatz map C has only finitely many cycles, and eventually the orbit of any natural number reach one of those cycles. But we don't know. It will be super nice to find a set of conditions that is not only sufficient but also necessary. Okay, so this is a reformulation of the main theorem that we were discussing a few seconds ago. For every epsilon larger than 0, you can find a constant C, such that this inequality holds for n in a set of logarithmic density close to 1, but it's smaller than 1. Okay, so I was saying that, of course, you can consider, so a few minutes ago, I mentioned that, of course, you can try to consider an even larger family of Collatz maps, right? For instance, this is a collection, this is a family of maps that was considered by these two authors, Matthew and Watts. You can define C in this way. And here, let me point out that the situation that we studied, the situation that we analyzed, correspond to this case. So what happened in our definition? If n is divisible by p, which means that this is equal to 0. So if n is divisible by p, we define the image of n to be n over p. So when n is equal to 0, q0 is equal to 1, b0 equal to 0 in our case, right? So which is what is written here. And all the other q's were equal to some specific value. So this is the situation that we study. Later, once we were done with our project, at some point we heard about this larger family of maps. And although we didn't think that much about this larger family, I should point out that in a first look, it seems that it's not possible to adapt our methods to this larger family, at least not in a straightforward way. So you will need new ingredients. So that's another interesting problem to consider. And I would like to mention that, in fact, Matthew and Watt, they conjecture that that this should be true. If you consider, if we assume that P and QM are coprime for all M, then whenever this inequality holds, all the trajectories, all the orbits are bounded and eventually gets inside of a cycle, and otherwise you have an erratic behavior. The orbits called diverge. I should point out that in our case, remember Q0 is equal to 1 and all the other Q's are equal. So this condition will be Q to the P minus 1 smaller than P to the P. which is equivalent to say that Q has to be smaller than P to the P over P minus 1, which is precisely this condition, right? Which is one of the hypotheses in our main theorem. So this will be, it will be interesting to extend our probabilistic results to this larger family of Collatz maps. Okay, so in the last few minutes, I would like to say at least, I would like to mention at least some ideas that help to establish our main theorem, although I'm not going to get too much into technicalities. But first of all, let me remind you. We already talked about this acceleration map, where what we do here is that we divide by P to the M, where M is the largest power of P, such that the largest power of P that divides this. In other words, M is the p-adic valuation of Qn plus Rj. We can try to, for a random, if we choose capital N in a random way, we may wonder how does this p-adic valuation behaves. So let me tell you that if you perform some q-adical, something that plays an important role is that we will perform a q-adical analysis. But let me mention that we can observe that the orbits of this acceleration map are kind of irregular. They don't behave like a uniform distribution. In fact, what we have is that what we can observe is that for a randomly choose natural number, capital N, the number of times that P divides Qn plus R, so which is what we have here on top, has a geometric distribution of mean P over P minus 1. So this number already appeared several times in some previous slides, and that this is precisely the reason. Okay, so let me explain how this map works, and then we will observe that what is the general form of this acceleration map. So first of all, this will be the first step, right? So the image of capital N looks like this: Q times N plus R1 divided by P to the A1. What is A1? The largest power of P, such that this is an integer, right? The largest power of P, such that P to the A1 divides this. If we apply this map S again, so if we iterate, then what we obtain looks like this. And we may think that, okay, again here, what is A2? A2 is the largest power of P, such that P to the A2 divides Q times N plus R2, right? So they are all defined in a natural way. So if we continue like this, what we can observe after in an inductive manner, we can obtain this general formula, this identity. This is a very nice formula for this for the orbit of the acceleration map. So we obtain this, and we made what happened is that this term, this one is basically the main term, the most important, and here we have some error terms. So let me focus our attention on the main term. In fact, dealing with the error term is very difficult, requires a lot of analysis, some geometric ideas, some renewal process. But let me at least say a few words about this term, which is the most important, the main term. So as I was saying, if we continue iterating this map, capital S, we will obtain a formula like this. So what can we say about this main term? So I already mentioned that this p-adic valuation behaves like a geometric distribution. So more precisely, like a geometric distribution of mean P over P minus 1. So that's very nice, because from this identity we can observe the following. So if we assume that the error term that we can control the error term nicely, so Sn will behave. So we can care only about the main term. So Sn looks like this, behaves like this, and since we mentioned already that this p-adic valuation behaves like a geometric distribution of mean P over P minus 1, we obtain these other two identities, basically. And so what happened here? If this product is smaller than 1, then we have a nice behavior, right? And if this product is larger than 1, we obtain, we expect an erratic behavior. So that's precisely why the reason why this condition plays a very important role. So whenever this inequality holds, we expect to have a good behavior, and otherwise we expect to have a bad behavior. In some examples that I mentioned at the beginning of this talk, for instance, we consider the phi n plus 1 map. In that case, if Q is 5, we are not allowed to take P equal to 2. Right? But if Q is 5, we are allowed to take, and P is equal to 3, then this inequality holds, right? Because phi is smaller than 3 to the 3/2. So that explains why for the map phi n plus 1, things were not so good. But in the case when we were, but in the second map, everything was nice, right? So, but anyway, so I think this is a good moment to stop because I don't want to get too much into technicalities. So if you have any questions, feel free to ask. Thanks for your attention.
Thank you very much, Jose. That was a great talk. Are there any questions? Christina has a question.
Oh no, I was just doing the clap emoji.
Yeah.
Sorry.
I'll ask one small question. There was this more general conjecture with Q0, Q1, etc., QP minus 1.
Oh, yes, yes. Oh, maybe, where was it? So.
It was, I think, at the very end with many.
Oh, here it is, here it is.
Yes. Do they explain where does this condition come from? Q0 times QP minus 1 is less than P to the P.
Yeah,
you had a different explanation. You had some explanation for this particular case, right?
Yes. For our particular case, as I was saying, the n term of the orbit of the capital N by the acceleration map behaves like this. So that's why we really want this inequality to be true, right? Because otherwise, if this is not true, this is larger than 1, and this is going to blow up, right? So for instance, that happened in the case when Q is 5 and P is 2, right? That I mentioned at the beginning. But and as I was saying, sorry. Oh, here it is. And as I was saying, our case corresponds to this situation when Q0 is 1. Q2, Q3, Q4, and so on, they are all equal to some particular value Q. So we get Q to the P minus 1 smaller than P to the P. So in our, I believe that we should be able to justify also using probabilistic methods. What I wrote here comes from the law of large numbers. So perhaps we can also justify that. But as I was saying, so we heard about this paper only once we were done, and we tried to observe if it will be kind of straightforward to extend our methods to this case. In a first look, it seems that that's not the case. There are some difficulties. So I think it's a very interesting problem. It's not just a straightforward adaptation. But yes, I am not sure. They conjecture this, but what they do in that paper is not really in this direction. So we didn't go over the details. But yes, this is an interesting. This is a super strong conjecture, of course, right?
Yes.
It's stronger than what we conjecture, and it's stronger also than the Collatz conjecture. So yes. But anyway, yes.
Okay, thank you, Jose. Any other questions?
Excuse me, may I have a short question?
Yes.
Sure, go ahead.
At the beginning, you said that for some numbers, like 27, the number of steps necessary to reach 1 is pretty large.
Yes.
I think it was 100 something, no?
Yes.
111.
Yes.
On the other hand, if you take, say, powers of 2, then this number is obviously small, like log with base 2.
Yes.
Are there any estimates if you take the first, I don't know, many numbers? What is the average? What is the average size of number of steps necessary to reach that? I see that here the graph is pretty wild, but
yeah, that's a great question. That's something which is not well understood. Yes, so it will be very nice to understand that better. But yes, there is no, at least not that I know. I related to that, I can mention that we have some numerical observations as well. Okay, let me go around here. For instance, let me talk about this, or let me talk about this. You may wonder also, you can ask questions like this. Okay, so I mentioned that for C2, it seems that these are the only 2 cycles. You can ask, what is the density of the set of the natural numbers for which you get into this cycle, and what is the density of the set of the natural numbers for which you get into the other cycle? So those are very interesting questions. And if you use numerical analysis, you can try to make some conjectures. But yes, that's something we want to explore further. But that seems to be also that seems to be very hard. But yes, understand. There are many interesting questions to be explored, or also this question. Okay, so basically the generalization that we consider is we divide by P when possible, and we multiply by Q and add some convenient R. So how many cycles are we expected to have, right, for a given map like that? So there should be, perhaps there is an answer depending on P and Q, right? We can say if P, depending on P and Q, the number of cycles that we expect to have is, you know, we can perhaps, maybe there is a nice result like that is possible to obtain, but yes, nothing is done related to that. So yes, there are still many things to be explored. Yes.
Thank you.
Of course.
Okay, I think we asked lots of questions, so let's thank the speaker again. I will stop the recording.